introduction. My name is Marta, as Herman said, and I've lived in the UAE for the past 10 years. I've always had a really strong interest in computer science and medicine, so I wanted my research project to be that intersection between care and innovation. But before I do get started with the project, I wanted to give a thank you to Dennis, my mentor, for the guidance. It was invaluable. So thank you. Okay, so on today's agenda, I'm going to go through the introduction, and that's just the way that my thought process went throughout the project. So how I identified a research gap, how my question was developed, because it went through multiple stages of development, the strengths that I predetermined, different aims, and just some context so that all the data makes sense later on. It's also important to note that the method and results section is combined, because my question is a comparative review. Each disease has separate articles that I researched. Therefore, each disorder has a different method. The discussion is going to be the actual comparison between all diseases, and the conclusion is just going to be any further research that can be done, as well as a little extension on ethics that I went through. So firstly, I'm going to be going through the research gap. Before you get started with your research, it's really important to identify what's already out there. So to gain that overview, I went on sites such as PubMed, Google Scholar, and JSTOR. So during my research, I found a lot of information on new AI models, because there's a lot of up-and-coming developments made in that field, so that wasn't very surprising. There was a lot of information on neurological disorders. Again, that's not surprising due to how vague that term is and how many disorders there are out there. In terms of AI implementations in healthcare, there was a little bit of research on that, but again, because AI is such a new field, it was hard to find articles that actually went into depth on that area. The first gap that I identified during my research overview was the lack of comparative articles. So yes, there was a lot of information on separate AI models, but I couldn't find any reports that went in depth for comparisons between them, as well as comparisons in the neurological disorders. The second gap I identified was the benefits of those implementations into the medical field. Because AI is so up and coming and has been developed in so many different fields, it's inevitable that it will be developed in AI medicine. So having that evaluation as to whether or not it is helpful for both hospitals, patients, etc., that was a really important overview to have. And finally, for neurological disorders, as I said, it's a very ambiguous term. So I decided to narrow down my search to 3 of the most common disorders, and that's epilepsy, glioma, and TBI, which stands for traumatic brain injury. Now, the development of my research question was something that I did alongside the research gap identification. As I was looking through multiple articles, I would note down any ideas that I had. My first question was on wearable devices and biomarkers, and even though I did really like that question for epilepsy, I felt there was too much research out there for mine to be unique to the field. My second question was a bit too vague for me. It went through overall neurosurgical interventions, post-surgery, which was something I was really interested in. However, because it wasn't specific enough, I felt it would make it really difficult to actually compile specific research on that. My third question was really specific. It went the opposite way as the second one. It goes through methodology, accuracy, data, all the information that makes AI models work. That's why I really liked that question. However, it only went into epilepsy, and even though that was one of my aims when researching, I didn't want to research epilepsy. I felt that there was no comparison that was able to be made, and since that was one of my research gaps, I needed to be able to tick that box. My fourth question, which was almost perfect, it went through AI, its limitations, its strengths, and it does go through multiple neurosurgical conditions. And so I felt that it was a good question to advance with. However, because I wanted a balance between AI and medicine. That was one of the most important parts of my project. I thought this one went too far into AI to give a good balance. And that is how I decided on my question, which is AI when predicting neurosurgery, post-neurosurgery brain recovery. And it's a comparative review between epilepsy, glioma, and TBI. When you're researching, there are so many articles out there, so much research right in front of you that it's hard to really focus on what your article is and what your question is about. And that's why it's important to predetermine your aims, so you always stick to your question. That was really important when I started my research. And so my first aim was on investigation and how investigation of AI is being used in neurosurgical conditions. My second aim was analyzation, about how methodologies and predictive approaches differ between AI models for conditions. My first hypothesis was on difference. Because the accuracies of each model will differ, the results are also going to differ. And my fourth hypothesis is about the difference in data accuracy and data scarcity. Each model has a separate purpose and therefore will use different metrics. That just goes to show that the data produced will be different per model. I looked at different strengths and limitations before starting my research. The first strength was that an increase in interpretation and explainability of these models is going to result in an increase in implementation into the field, and that's the ultimate aim when it comes to researching AI models in medicine. We want to get to the point where all models are as accurate as possible for the patients. Secondly, my research gap was identified. It allowed for my research to be unique to the field. Thirdly, I listed the 3 most common neurological disorders. Because there are so many disorders out there, it's hard to really be specific as to which ones you want to research, but because the 3 that I went for, they are one of the most common disorders, that means that a lot of people are affected, and therefore the models and the research that has been done is going to help a larger variety of people. And the final strength was the benefit for future models. If there's more research out there, programmers are able to develop and constantly develop these models to make them as best as they can be. In terms of limitations, I found 2 main limitations. The first one was the idea of data imbalance, because that makes comparisons quite difficult, and as you know, this is a comparative review. The second limitation was the idea of brain activity recovery. If we think back on my question, that term is used in the title. Because that's such an ambiguous term, I had to be able to define it, what I wanted it to be like in my research paper. And so for that first challenge, for data imbalance, what I did is I implemented certain evaluation frameworks and I stated my biases. So as I was researching, if a paper didn't match the guidelines that I wanted it to, I would automatically eliminate it from my research pile. For the term brain activity recovery, what I did is I looked at neurophysiological, neuroimaging, and cognitive measurable domains. So these are the 3 ways that doctors are currently measuring brain activity recovery, and you'll see that they're being used in the AI models as well. To give a little bit of background on AI and neural networks, this is an idea of a neural network. It sounds very similar to the neurons in the brain, and that's because when programmers made AI and neural networks, they had the idea of the brain in mind. They wanted to mimic the way the brain can learn and adapt, because that's the ultimate goal for AI models. The first disease we're going to go through is epilepsy. So epilepsy occurs when atypical electrical signals cause seizures, and that can range from really harmless seizures to really harmful ones. 50 million people are currently affected by epilepsy, and 75% of which aren't receiving proper treatment. That's because of low-income areas. 60 to 70% of the people who are able to afford that treatment, they end up with seizure freedom, which means that they are technically cured from epilepsy. The causes of epilepsy vary. Usually it's inherited, so it's genetic. Some can be caused by infection, but some of them could be idiopathic, which means that the cause is unknown. The surgery that people undergo when affected by epilepsy is the SOZL surgery, and it's more of an exploratory surgery in the terms that you have to remove certain brain areas that are allegedly causing that epilepsy. It's a really hard surgery to do because the brain is so complex and the sections in the brain that affect seizures will be different for everyone. If there is harm during the surgery to the brain, that can result in 25 to 50% of people occurring a decline in verbal memory, as well as 25 to 30% of people resulting in word-finding difficulties. As I was researching my model for epilepsy, I went primarily for Google Scholar because it gave me a larger amount of articles. The keywords that I used when researching were graph neural network, seizure freedom, deep learning, and stereo EEG. If you remember back to the frameworks I used, stereo EEG is one of them. So originally there were 111 articles that came up. Of those, I found 8 were the most applicable to neuroscience and AI. And of those 8, 4 of them matched my question. And you can see the titles are listed on the screen. Because I wanted my research to be as specific as possible, I decided to choose one of the articles and go into more depth in that. So that article was graph-based deep learning on stereo EEG for predicting seizure freedom in epilepsy patients. And the model is called the GNN model. So the GNN model will take local and global features of the brain, and it will take as much data as possible in order to predict both seizure freedom and brain region identification. What that means is that the model will not only predict which areas of the brain are causing those seizures, it will also predict what the chances are of seizure freedom afterwards. And so that allows for PM, which stands for personalized medicine, to take place. Personalized medicine is where you tailor a treatment towards the patient. So if the chances of seizure freedom are really low, then rehabilitation can be set in place so that the patient can go straight into that rehab, and that allows for the best treatment and the most effective treatment for those patients. On the findings, you will see that there was quite a lot of data published. An F1 score is the amount of false positives shown. So the lower the F1 score, the higher the amount of false positives. And because it's 91.2%, it shows that it's really accurate. In terms of accuracy, we have a 91.4% accuracy, which speaks for itself, as well as the precision of 91.5%. When looking at recall, that's really important for AI models. It means that it can go through new data that it's never seen before and produce the same amount of results and the same accuracy of results every single time. And that recall was 91.4%. The study's conclusion was the fact that brain connectivity, which is all the research has taken, it excels at seizure freedom predictions. I took that discussion to mean that additional harm can be reduced through the treatment of GNN models. I just want to state that there will be QR scans on every single slide, so if you want to follow along, it will take you to the original source. Secondly, I'm going to be going through glioma. For those of you unfamiliar, glioma is a sort of brain tumor, and it occurs in clumps and clusters, so it's multiple tumors forming at the same time. Brain tumors are obviously a really harmful disease to have, and gliomas take part in 45% of all of those brain tumors. They occur due to mutations in the glial glands. It affects 6 per 100,000 people annually, and in the less severe cases, patients have a 10% survival chance after 5 years. However, in the more severe cases, patients tend to last 12 to 18 months. So it's a very serious disease. There are many surgeries that can actually help cure glioma. However, the most common is a craniotomy. Craniotomies usually result in 55% unchanged patients, which means that there is no additional harm done to the patients. However, 24% of people do result in memory impairment. 13% of those get hearing loss in either 1 or 2 years. Overall, there has been shown a decline in cognitive intelligence. In order to research my model, I used the key terms deep learning, fusion, multimodal, biomarker, and glioma survival outcome prediction. To quickly go through what some of those key terms mean, multimodal was a really important term that I used. Because glioma is such a serious disease, patients give a lot of data to their doctors so that they can make the most accurate diagnosis possible. And that means taking information from multiple nodes and multiple sources. And that's why the AI models that treat glioma are similar in the sense that they take information from so many different places. A biomarker is used for cancer prediction. So a biomarker can be your breathing, your heart rate, all of those slight changes, which could mean very little. They actually show whether or not your tumor is developing for better or for worse. And so originally there were 470 articles, 27 of which actually applied to neuroscience, and then 5 of those I selected based on how well they applied to my question. So all 5 articles are listed on there. And again, I only chose one. I chose the Deep Orthogonal Fusion Model, also known as DOF model. And it is a multimodal prognostic biomarker discovery. It integrates radiology, pathology, genomic, and clinical data. So automatically you can tell that data is taken from multiple different places. Radiology is when the MRI scans and any type of brain imaging is taken. When looking at pathology, it's the tumor grade, the size, the shape. For genomic, it's just your IGH mutations, any sort of cancer mutation that occurs. And clinical data is just your personal information. So the study's aims were survival outcomes. This model aimed to predict how long patients would survive and whether or not they would. So it measures risk for survival prediction. This again helps post-op care for rehabilitation to take place to help personalized medicine. The findings were a C-index of 0.718. What a C-index measures in AI is a strong predictive performance. So as you can see, it's a really strong predictive model. Its conclusion was data modality and how using information from so many different sources can actually help prognostic information and diagnosis. For discussions, it just shows that DOF models have the potential to improve clinical decision making. Lastly, we have TBI, traumatic brain injury. TBI affects 70 million people annually, and it is the leading cause of death for people under the age of 45. This can occur from any type of trauma to the head. It can occur in sports accidents, traffic jams, etc. However, the important statistic to note here is that 50% of people who get TBI, they usually end up with a long-term disability. Similar to glioma, TBI can be cured with a craniotomy. However, it is a decompressive craniotomy. What that means is that brain swelling is decreased. That's really important for TBI because that is the reason why so many patients unfortunately do not make it. The causes of any harm during those surgeries are the leak of spinal fluid, as well as infection risks. There is a 9.1% chance of meningitis during this decompressive craniotomy, and even though that's a very low chance, it's still a chance that it could occur. And finally, there could be any cosmetic deformities, and that just refers to any aesthetic changes that could be made. I use the key terms functional, AI modeling, TBI, biomarker, and prediction. There were 165 original articles. I narrowed that down to 13, and only 4 of those actually mentioned post-neurosurgery predictions. Again, I chose one article, and that was the leap to ordinal detailed functional prognosis after traumatic brain injury. And it's a flexible modeling approach, which I will explain in a second, but it is important to note that the model is called the Deep TBI model. So the idea of a flexible modeling approach is that the results aren't quantitative, they're qualitative. So you don't end up with a statistic per se, you get classifiers in word form, And so the study's aim was to predict recovery in the first 6 months, and that takes data from the first 24 hours of admission into the hospital. That's very similar to what a doctor would do. When you're working with traumatic injuries, the first 24 hours are crucial for diagnosis. The C index was 0.76, which again just means a strong predictive performance. Going back to the idea of qualitative modeling approaches, there is an 8-level GOCE scale that doctors still use. And what it is, it's a scale of how severe the TBI injury is. So you can have a 1, which shows that it's minimal risk, but you could also have a level 8, which is very, very severe risk to the health of the patient. The overall discussion is that a full spectrum of qualitative outcomes is really important for recovery. In terms of the discussion and comparison, you can see that there's no real overlap between each disease. Epilepsy goes more for the GNN accuracy, precision, recall, F1 score. And even though both glioma and TBI refer to C index, the C index in TBI is ordinal, which is a more developed way to measure C index. So that left me with the question of how could I compare them to make a comparative review. What I did is I took the data from accuracy in C index and ordinal C index, and I converted it back to its clinical definition. So accuracy, for example, is strong predictive model. And I compared those qualitative samples that I got, and that showed that the GNN model for epilepsy is great at surgical decision making. The glioma model, the DOF model, is better for long-term outcome predictions, and the deep TBI model for TBI is the best at prediction analysis abilities. In terms of future research that can be done, because AI is such an up-and-coming field, there's constant development. The aim is for dataset sizes to increase and to become more varied. Because AI isn't inherently biased, whatever you put into the dataset, whatever you input to the model, that's what it's taking into account. So if your dataset, if it isn't varied, if it doesn't have that much information, then there are certain limits to what the AI can predict. And that's why there needs to be more development in how much information doctors are inputting into the program. Another extension that I wanted to go through is the idea of ethical guidelines in AI. AI is such a new level to healthcare that the current ethical guidelines that we have, for example, the 4 pillars of medical ethics, which are beneficence, maleficence, autonomy, and justice, they're not necessarily applicable. So we need to start looking at interpretability, the training of certain doctors, and just any type of explainability that we can add to the field. Just to showcase my references, these are some of the references I used to write my paper. Thank you.
You mentioned by glioma was that it could be put into the medical use or clinical use quite quickly. I was wondering for that one and the other ones, does that mean like soon, like in terms of like a decade or shorter period of time?
Yeah, I think definitely in the next decade or so there's going to be additions to the medical field, because glioma and TBI, for example, they're really well-researched fields. There are constant developments made to the AI models, and that would just allow for implementation to be made. The only problem, which I was mentioning at the end, is the idea of making it explainable. Clinicians are not going to want to implement a model into their field if they don't really know how it works. They would rather have a more interpretable one there. So just being able to develop these models and have more research done, that would be the #1 thing we need to do to speed up that implementation.
And my second question was about like, you said how like the AI model would be put for medical use, like specifically in medical fields. Like, I was wondering, like, would there be ones open to the public, and if there would there be like dangers of false information, or would they just cut out the idea that they could be accessible to the public?
So the idea is for these programs to be added to the current network that the hospital has. So these aren't machines per se, they're more programs you can download for every single computer. So I would assume that a training period would be done first on certain patients that would agree and consent to that. And then if the accuracy and the outcomes that they have are more beneficial than the ones they had with current models, then I would assume it would become more open and the norm in hospitals. Yeah.
Could there be a social or environmental impact on this?
Yeah, so especially a social impact. A lot of people don't necessarily trust AI, especially when it comes to healthcare. For me, because I've researched so much AI, if you gave me the option between a doctor and a good AI model, I would most likely go for the AI model, which is why when I was conducting this research paper, I opened up the discussion to a lot of my friends and classmates, and I realized that a lot of people are kind of against that AI implementation, and that's mainly due to the idea of not knowing what's going on and where your data is going. So having protection laws against your data and your privacy, that would be the number one issue that we would have to sort out first.
What type of data specifically is used to input into the AI?
So when you're looking at glioma, for example, you would put all the information you get from MRI scans. So for tumors, you could have the tumor shape, the size, the tumor grade, and all of this information which a doctor would see. It's all of that information put into data and quantitative terms, and that's input into the AI. Programmers tend to add as much information as possible because they don't necessarily know what's going to be the most helpful for an AI model.
Are these AI models already widely used in hospitals?
So the ones that I have researched aren't used in hospitals yet, but there has been a lot of implementations in testing centers. So it's not necessarily open to the public, but it is in the process of doing so. Yeah.
You mentioned about AI and recovery. Is AI about able to help in recovery, or how does AI work in recovery of patients after surgery?
Yeah, so the idea of recovery is what the doctor and the medical team can do to help recovery afterwards, so to help the best outcome for the patient. And what these models do is they predict survival chances, which areas of the brain are most affected, and that just shows how much more processes and treatments need to be done on the patient post-surgery. So if the area highlighted on the brain region is harder to get through surgery, then the risk of survival could be a lot lower. It could be really hard for survival to take place. And that just lets the doctors know what procedures might need to be done later on. Yeah.
If this was an option to either a human would do this or AI, which one would be more expensive? A more expensive treatment?
Yeah, so currently for the US specifically, AI models are more expensive, especially because insurance doesn't necessarily cover newer models, and that just goes to show that there's not enough explainability or trust in AIs yet. So I would assume that once there's more research out there and it's more trusted by clinicians and hospitals, then there would be packages and insurance companies that would allow that AI to be covered. Yeah.
How does the AI predict the probability of seizure freedom in epilepsy patients, and what information does the AI need to predict this?
So the information the AI takes is anything from familial history to the information that doctors are collecting once the patient comes in, and what seizure freedom, how that's calculated. Basically, certain areas of the brain are highlighted, and that area is removed to remove the idea of epilepsy occurring. So seizure freedom, if there are multiple areas in the brain that are affected and are the root cause of that seizure, then the risk of seizure freedom, the chances of that are a lot lower. But if it's in a very accessible place in the brain, and it's only a couple sections of the brain, then that would bring the seizure freedom chance higher up. Yes?
If this was to be applied in the future, in a decade or so, or less, would what people are learning in school, if they were doing the medical field, change what they were learning right now? So if there was new results that would help spot patterns?
would they learn some new stuff?
Yeah, so medicine is an inherently changing field. When you go into medicine, you're expecting to adapt for different procedures that are being done. So as procedures are changed and updated, the doctor is expected to keep up with that, and medical school curriculums will most likely change because of that. Yes? Either.
Since AI is made using the same kind of idea as human neurons work, then if someone gets a brain injury like TBI, could AI be used to predict how to heal it?
How to heal?
Yeah.
Yeah, so AI, it uses the same idea of brains, not necessarily to replicate the human brain, but replicate how that brain learns and adapts. So that's what makes AI so accurate. It can be used to help heal TBI in the sense that it will highlight which areas are most impacted, but it won't be like a replication of the human brain, and it will show you which areas.
All right, let's do one more question from the students, and then we'll move on to Dennis after this as well.
What other neurological diseases or dysfunctions could be helped using these AI models?
So there are so many neurological diseases that can be helped. I just looked at epilepsy, glioma, and TBI because they're so common. But for glioma, for example, that's just one type of brain tumor. Any type of brain tumor can be helped using a similar sort of algorithm.
Dennis, go ahead.
First of all, thank you so much for this really nice Marta, you have done a really tremendous job during these last 2-3 months. It's been amazing to see your progress through the project. Coming from the developmental neuroscience field, I was wondering, do you think that this AI models are also applicable for children, for example, like brain development in this area? Do you think it can be applied there also?
Yeah, each neurological disorder, it's most likely to affect a certain age group. So even though the AI models aren't specific to ages, because epilepsy, for example, it's more common in children and early teens, that AI model will be helpful for that age group. Again, it's the idea of data sets being varied and having the largest amount of data possible, because if you have 1 or 2 pieces of information from adults, but a lot from children, then that diagnosis could be less accurate for the population at risk.
Perfect. Well, one sec. Bea, go ahead.
Yeah, sure. So some AI models can not only make a prediction, but they can also tell you how certain they are about their prediction, which I think could be very useful in the medical field, for example, so that the practitioner knows, okay, should I really trust the AI model or should I use more dynamic reasoning? So do any of the models that you looked at also provide kind of a measure of certainty about their prediction?
So the models I looked at didn't provide certainty, but there are a lot of others that I listed that did. That's really helpful for the medical field, as you said, because it gives you the ability to choose whether or not to carry on with the procedure. So I would assume that with current developments, because I know that the glioma and the TBI models are currently being redone to make it more interpretable, I would assume that that's one of the additions that they would make.
Perfect. I'll take the last question. Thanks very much for the awesome presentation. Great work. I was really curious, just in general, what you found the most surprising thing from your personal research journey in this field.
I was really surprised that TBI, traumatic brain injury, was so common because you see the news and you see all that information and you think, oh, it's adults that are being impacted. But when I saw it was people below 45 years of age, there were a lot of articles that actually talked about teens and teenagers, so I found that really surprising.
Perfect. Thanks so much. Let's give Marta one last and enjoy the rest of your day.
Yeah.
AI model could be more effective. Well, that's a good question. Can't take it. I believe.
I'll do it. Yeah.